Hey, we're gonna play a little more with this little windmill. There are a couple videos on YouTube that I've already made a few months ago, but I think today, if we don't run out of time, we're gonna put it up outside and kind of test it. But before I do, there are a few things to go over. I'm gonna do a real quick recap on the nature of the turbine. These discs are 4-inch diameter, made out of 1/8-inch steel. There's one in front and one behind. Each disc has 8 of these magnets. 1-inch diameter by 1/4-inch thick neodymium iron boron N42 grade, and they're put on there north south. Opposing poles opposite each other, so that's pretty typical for these axial flux alternators. There's 8 magnets, 6 coils, so that you get 3-phase output. These coils have, I think it was 160 turns of 22 gauge wire, and they look about like this. And they're wound just, I made the hole a little smaller than the magnet. You don't want to go, there's not much point going too small. It's not optimal use of space. The tiny windings don't induce much voltage, and they add resistance, so I go a little bit smaller here. Thickness of the coils in this case was 3/8 of an inch. And these are tight. I actually pressed these coils really tight. I'm kind of surprised they didn't short out. I pressed them so hard to get them thin, but it worked out all right. So first test of an alternator like this is you could short it out and it should get quite stiff to turn. I'll just do it with my pocket knife. But if I get that spinning good, you might even see a spark. It really puts the brake on hard versus free spinning. This alternator is set up on 2 1/2-inch bearings, and I just welded this bracket back here. Disappointing problem with this design is the 1/2-inch ball bearing back here. If I tighten this as much as I'd like to, it's actually squeezing this pipe, and it squeezes the bearing and makes it a little bit stiff to turn, so it's not real tight. Another design consideration here is you'll notice I've got this tipped slightly back away from the yaw bearing. This is the yaw bearing. That's to keep the blades out of the tower. I'll do a quick test, rough test of the alternator. First, I'll check resistance. Knowing stator resistance is important to know alternator efficiency. In this case, I'm getting a rough reading of about 3 ohms. It's hard to read resistance because, 3.7 ohms. And if I short the leads, I get about 0.2, so figure 3.5 ohms. Checking resistance is tricky because any voltage this generates, even vibration, if I wiggle it, it'll throw the reading way off. 3.7 seems to be. So figure 3.5 ohms. Next test, AC voltage. I'm measuring AC voltage of alternating current of a single phase. Voltage is directly related to the rate at which the magnetic field changes. So if if I check it at 60 RPM and I get a certain voltage, then I know that at 120 RPM I would have exactly double that voltage, and so on. So here I'm just going to go around once per second. I'm going to estimate once per second. Actually, I'll get a stopwatch and then I can do exactly once per second. Okay, I got a stopwatch now. So there we go. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6, 7, 8, 9. So I get about maybe 2.5 volts AC at 60 RPM. It's a rough figure. I could use a tachometer. This is a laser tachometer, but it's kind of hard to read, hard to position. It becomes a two-person operation to do this. In previous videos, we did some stuff on the milling machine that was a little more precise, but I'm just kind of going through it all again. You can get pretty close using a stopwatch and counting 1 or 2 RPM, 1 or 2 revolutions per second. Next thing to consider is direct current voltage, which will be higher because I'll show you here. What the meter's reading is RMS AC, which is AC. It's the average voltage under the curve of a AC alternating current wave. So the average voltage under this curve is somewhere here. So if I'm reading 2.5, when I rectify this to direct current, I'll be rectifying the peak voltage, and that'll be 2.5 times the square root of 2, which is about 1.4. So I'll check, do this. Oh, but the other thing is, in the diode here, I'll have about 1.4 volt drop. Each diode will drop about 0.7 volts, and it's always going through 2 diodes. So when I rectify this 2.5 volts, I should expect a bit more, minus 1.4. So it'll actually come out lower. But when we get up into real voltage, like charging a battery at 12 volts or something, the rectified voltage is quite a bit higher than the AC voltage. So in other words, if I'm charging a 12 volt battery, or a 12 volt battery will start charging around 9 volts AC, because the rectified, that's going to come out to close to 12. Quick video, I'm really fudging some numbers here. So I'm hooking up a 3-phase rectifier. There we go. Now I can look at direct current. Yeah. That's probably good enough connection. So now I'll change my meter to direct current, DC volts, and And there we go. So, back to the stopwatch. Can you fix a stopwatch, Maya?
Maybe.
Okay, now looking at the stopwatch, I'll go once per second. And I'm looking at direct current. 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually, it's coming out right about the same, right about 2.5 volts, because I lost 1.5 volts in the rectifier. It's funny this one's working out that way, but if it wasn't for the rectifier loss, we would have about 4 volts now. And that 1.4 volts doesn't change as the output changes. So at 120 RPM, I'd be at about 8 volts minus 1.4. So we'd be at about 6.6 volts at 120. At 240, then we'd I don't want to do the math, but I think you get the point. The 1.4 is constant. The rest of it is directly related to RPM. Next thing we'll do on this turbine is I'm going to fit the blades. And I think I have all the bits here to do that. These are wooden blades that my friend Rich made on the CNC router. They should be pretty good, pretty accurate for about a tip speed ratio of 7. If you don't know what that means, maybe I'll shoot another video someday and talk about that. But they're nice blades. I put them together on these thin plywood hubs. Got these little spacers here. This is a fun little turbine. I kind of wonder how it's going to work. For its size, the alternator for this blade is 1 meter diameter. The alternator is really quite powerful for a 1 meter blade, and I would expect it to stall the blades unless the load is well matched. But directly tied to a battery, this alternator is too powerful, too efficient. I can try to explain that more later. But one way to get around that is adding a bunch of resistance and make it less efficient, basically. Or I could use an MPPT controller, which we might do. These washers don't fit. Oh, that one does. There's no room for lock washers. Snug those up pretty good. Could be tightening all this together, things get stiff. This alternator has a really close gap between the magnets and the coils, and I actually think it would work a little better. It would fall into a better power curve if I opened it up a little bit, but that's tricky. I didn't design this alternator for any particular load. It's way too, the voltage is way too high for a 12 volt battery, unless I use an MPPT controller. So if we hook this straight to batteries, I'm probably going to do 24 volts. does it feel? Cool. Okay, blades on. One concern is always blade balance, and the blade balancing is especially tricky with a tiny blade. Reason being, the centrifugal force is related to the square of RPM. So the smaller the turbine, the faster it spins, but also the harder it is to balance. So it cares more about the balance the smaller it gets, but it's also trickier to balance. The way I normally balance blades, I've already kind of done this one. One way to do it is put the blade on the turbine, and if it's very free spinning, the heavy spot will come to 6 o'clock. So originally that might have been the heavy spot, and I added weight here so that it balanced out this way. And you can add a weight and see what happens, and if it still moves, move the weight out or add more weight. It doesn't take very long, and it's fairly easy to do on bigger turbines. On a little one like this, it's kind of hard to know. And I've got it close, but I know I think it wants, you can kind of tell by just bumping it. Or you can tell by adding a little piece of weight and seeing what happens. I think it wants a little bit of weight here or here, because it comes back. Let's see. So I want to add a little piece of weight here. See what happens. Another way to balance the blade is to hang it from the dead center of the blade on a string, or if it's a big blade, on a chain, and get a level and add weight on it until it hangs perfectly level. And that's a good way to do it, but a little hard on this because I don't trust that these are dead center. And plus, if the alternator's a little bit out of balance, doing it this way is also balancing the alternator. I'm just going to cut a little piece of lead. Lead's real soft, so it's easy to drive a screw right through it. I'm just going to put a little piece here and see what happens. That was too much. What happens if I go here? I'm going to tag that there for fun and see what happens. We're not going to get it real good. It's going to shake because it spins so fast. Okay, now. Oh, that's very heavy, isn't it? Bad idea. Maybe I should just run with it the way it is. Another thing I can do is bend this and play with it like this. Get a motion. Could be I did an okay job first time around. That's interesting. That one didn't do anything. Still makes me want to put a weight here, doesn't it? I'm just going to tag it over here and see. That's opposite the weight I already put on that. It doesn't make sense. Obviously too heavy here now, so off it comes. I'm going to play with it the way it is. If I'm really careful, one way I can play with it and get an idea just how obnoxious is it. I got to make sure I don't break something here. There's not a lot of clearance. Hey Mike, could you start that fan? One click on the chain. I can tell the vibration here soon. It takes a little bit for the proper aerodynamics to kick in, but they will. So it's wagging a little bit, but not too bad yet. Probably run like that. So, while the fan's running just for fun, I wonder how high that wind speed is. I'll be right back. Okay, so I've got this cool little anemometer set for miles per hour right now, just to get some idea. Right behind the blade, I'm showing about 5 miles per hour. You can see how fast it drops off here. It says 12. But that's not really a good indicator, because if I come out here to the edge of the blade, I've only got 3. So this rotor is really not getting a fair wind treatment. It's getting loads of wind right in here at the center, but out here it's getting very little. Of course, most of your power comes out here. On a wind turbine, about 90% of your energy comes from halfway out here. Anyhow, it's not shaking so bad that I'm afraid to fly it. Next thing to look at that I'll just talk about briefly is this machine is a side furling machine, and it's the reason I built it like this is to be sort of a model of bigger machines that we build. But if you look at the geometry of this, the machine turns this way. The tail tilts into the wind. The tail is offset to the side crooked, which looks kind of funny. The reason the tail's offset to the side crooked is because the alternator's offset to the side the other way. So when the wind hits the rotor, it's always trying to turn the turbine out of the wind. But when the wind hits the tail, it's pushing it back. And so this is a compromise, hopefully holding the turbine square to the wind. In practice, I find it's hard to get it dead square to the wind, and sometimes I make a compromise for appearance, actually, and settle for the fact that it might be running a little bit crooked if the wind is coming this way. But this is a pretty good setup. We'll see how good it is when we fly it on the tower. If you look at the tail, it's on a hinge, and it has a chain to hold it here. Without this chain, the tail would wag over directly in line with this pivot. So it would be hanging over here. So the chain is holding it where we want it. In a high wind, the force against this and the force against the tail becomes strong enough to fold it up so that the tail is lifted because of this crooked hinge. And that really is the whole governing system. So in a high wind, if it's coming straight at the machine this way, once it gets up to a certain speed, which is determined by the weight of the tail, it will start to fold up like this. So that the wind against the tail and the wind against the rotor will balance out the force, and it'll run like this. In a super high wind, it'll fold up all the way like this. And we need to have it designed such that I've made some machines where accidentally the tips could get into the tail, but that can't happen on this one because it bumps into something here, I guess. Oh yeah, bumps into that, so that saves it. But it's got to bump into something to keep the tips out of the blade, or the blade tips out of the tail. So that's how the furling works, and that's how all the machines that I make work. So the next step, that kind of covers this machine. We'll shoot another video about setting up the tower, and we'll put it outside and see how it runs with the load. And I'll talk a little bit about tower geometry and tilt-up towers. We did make this tower here for it. It's 8 feet tall. Again, this whole thing is kind of a toy to demonstrate how bigger machines work. That said, you can buy commercial turbines this size, so it's a little bit more than a toy, but really this is a toy.